So we're going to talk about to grow a bit. First, I'm going to talk more how it's started, which sensors that we have, how they work. Then Maxime is going to do some base graphs, which can explain, okay, what can you expect from the measurements? What information can we see from it? And then we go over the data of B over Beek and the experiments we're doing there, where we are checking untreated plants and treated plants with AQUA4D with our measurements and see which differences that we can see. I said it earlier, but if you have any questions, just type them in and Maxime or me later will answer them directly. Okay. So it all started at the University of Ghent. There we have a professor named Kati Steppe. She's a rather famous professor in her field. And she saw, okay, during experiments, there are also always the same issues. With thesis doctorate students, while doing experiments, they saw that their measurements that they were doing, such as stem thickness, for example, they are always subjective. If someone else does it, it most often has another value. We saw it at another grower this morning as well, that when one person does the head thickness is always higher in number than the other one. So like that, it's a real subjective number. However, the trend can maybe be apparent, but still it's not really trustworthy. Also, most often such measurements are being done once or twice a week, also by different persons. And if there's weekends, it's not possible to measure. So there's all kind of trouble doing manual measurements. Definitely when we are measuring fine variations, such as the AQUA4D system, these are really small changes that you cannot see maybe in real time. Maybe at the end of the season, there will be some differences between both crops, treated and untreated. But yeah, it's interesting to have a continuous objective measurement. So she was sat with that question, and then her husband Dirk, luckily he's specialized in hardware, and he came up with a solution of measuring both SAP flow and stem diameter, and he developed this over 6 years of research. From this research, Phyto-IT started, a sort of spin-off with the University of Ghent that tried to distribute the systems commercially. However, he tried this, but unfortunately he failed somewhat. He tried for 3 years, but only got 5 customers. That commercial talent was not really his thing, I guess. So Pebble, which is a group, an incubator, an accelerator, is a trendy word. They saw the potential because they have a vision to, we need to better the planet. Everything that is, makes the planet a better place is something they are interested in. And then they heard the story of Phyto-IT at the University of Ghent, so they invested here and they started To Grow. To Grow is actually a more commercial entity that does the direct contact with the customers, but also the knowledge development. And Phyto-IT is now more a development company, so R&D. He develops our sensors and we put it in the market and we have contact with everybody about this. It's fun because young dynamic people are on the steering wheel, and like that we see that's really successful over 2 years and 1 or 2 months. We have gathered around 100 customers actually, because this is an old number. Like Looye is rather famous with their honey tomatoes, Royal Pride, Combivliet, but also Delphi, which is a knowledge center. They're really gonna be our knowledge base, to say it like that, and they are gonna see, okay, what is good, what is bad, and create certain values for us, because they see a large benefit from the sensors. But sometimes it's still not clear what the grower can do with it. It's a question we get sometimes. However, we see every action. It's sometimes difficult to say, okay, it's good that it grows or it's bad that it shrinks. These are base things, but we need more knowledge. So Delphi is our partner in this. So if you look at the past, how growers work, they almost often do all action based on past experience and assumptions. So we see that in the past this was fine, but with the increasing demand and competition, more and more there's more and more demand for an increase in efficiency. Otherwise, they die out, to say it like that. So yeah, today we have all this kind of sensor technology and other measuring basics. However, most often these sensors work on a climate level. There are not a lot of continuous measurements being done on the plant itself. So this is actually where we try to come in and try to measure the plant itself and to really say, okay, this is how your plant is reacting. Because there are some general rules like early watering is vegetative, but you see that this is such a linear way of thinking, which can have much improvement. So we try to give a more dynamic way of growing and see, okay, this action has this effect. I think we need to use
Okay.
Great, great. Thank you. So yeah, by seeing how the plant truly feels and reacts to every action in the greenhouse, we try to make room for harvest predictions, some insights into root quality and optimization towards the culture. Additionally, for systems like yours or lighting manufacturers, our system or our sensors can work as a sort of objective measurement that
Olivier,
can show.
your
Yes.
screen is not share. Could you share it again?
That's weird because I'm seeing the graph on the screen of Maxim. I stop presenting and I'll restart it.
Okay.
Can you see it?
Yeah.
Okay. So yeah, we try to optimize and really show an objective measurement to show, okay, this is the influence of this lighting schedule or this spectra, but also of the treated plants with the AQUA4D system. Okay, and how do we do that? Is by measuring the SAP flow and the stem diameter using these two sensors. This one is wrapped in a lot because of installation, but I'll come back to that later. So these sensors show changes in the environment. Every action has a sort of influence on the plant that we can't measure on the moment it happens, but we try to visualize it and show the grower, okay, you do this in the greenhouse and this is the effect. And later we're going to show some base examples that's going to explain what what they do. Also, plant actions such as pruning, harvesting, these are things that have an influence on the plant that we can't really, we can't see a bit, but we monitor in real time, and like that we can visualize it again. So these sensors are suitable for a growing season. They can, once installed, they can normally remain on the same place. However, the diameter sensor is sometimes prone to pushes. So it could be that you need to change it, but at the base of the plant, even in tomato where there's constant changes and lowering of the stems, normally they don't get a push. However, it sometimes happens. These sensors are suitable for herbaceous plants such as tomato, cucumber, eggplant, and bell peppers, but also woody plants such as grapes, but also blueberry, kiwi berry are things that we've measured before, and they are really suitable for it. And we see very good variations, even in woody plants, which was not something that we expected at first. Then they are both suitable for indoor and outdoor use. Generally, we have an idea, okay, a plant between 5, maybe 4, and 20 millimeters thickness in stem diameter is measurable by our sensors. This is a sort of general rule. However, yeah, there are outliers that we've tried before and they work as well, but it all depends on the plant itself. We have micro sensors in development, however, for crops such as strawberry or flowers, which are really fine stems that we can measure really clear with this, because the stem diameter sensor is a bit heavy. So if you would install it on a very small stem, it could break. The same with the SAP Flow sensor, as it needs to really be well insulated. It takes up some space. So if we look at how a SAP Flow sensor actually works, I included in because I know Charlie was rather interested in them during our last talk. So this is SAP Flow sensor, which is encapsulated around the stem. So I know previous SAP Flow sensors work with needles and sort of heat pulse mechanism, but these sensors are just put around the plant, totally non-invasive. So it doesn't damage us and make sure that it's a representative plant when we are comparing to the rest of the greenhouse. So this is a heating element. This heats up the plant very, very little, and the sap flow, the sap inside the stem. So what happens as the sap flow progresses through the stem upwards, it takes up a certain amount of heat with it. And by measuring with the thermocouples the temperature, we can measure how much heat gets transferred away from the sensor. And like that, we know very accurately how much sap flow there is at any given time. So we measure in real time. Every 2.5 minutes, we show measurements. However, this can be speeded up or slowed down if preferred. This is a diameter sensor. It's actually an LVDT sensor, to be exact, if you're interested in that. It measures a linear displacement on the stem or of other things. So this is just put around the stem. And then with elastics, we put it around to really fasten it with white rubber stretches, exactly. And then this needle is pushed against it. This system measures variations smaller than a micrometer, which is really needed to see the different potentials in the cells and really show those micro variations that we like to see during the day. We also install on a certain vein. If you know tomato plant, it's not completely round. So we try to put it on a more thicked area. And like that, we have more variations. Every plant has its own installation place, but it's rather easy, to be honest. Sometimes it can be bad data, but then you just need to replace and then probably will be good. So these both sensors are attached to our logger, our green unit here. This sends out these data every 2.5 minutes through the mobile network. So there's no need for Wi-Fi or other internet services in the greenhouse. And we see it more as a sort of plug and play system. Just install, put the logger online, and it connects to the mobile network, and the growers are ready to go. This is a more practical example of the logger installed at the pole and with the sensors around the plant. Here you can see a system in practice. As I said before, the SAP Flow sensor is very well insulated just because we need to keep the heat inside, but also keep the exterior heat outside for the most accurate measurements. So there's no interference with outside climate conditions. So now following, we have some base graphs which show a bit from, okay, what can we see in the measurements and what can we expect from it? Which benefits do they have? Maxim?
Yeah. Okay. Okay, so I'm just going to go through the basic graphs so you have an understanding of what the graphs are showing and how we can improve, of course, on one side for the grower his crops, but on the other side, how also we are able to prove that AQUA4D is working, for instance. So what we basically see in a day is when the sun comes up.
Merci.
So when the sun will rise, we will see that the SAP flow, so the white line, is going upwards. This is because there's more temperature, and also the radiation is actually the main driver for SAP flow and for photosynthesis. At the same time, we will see that the diameter will start to shrink. This is because actually what we are measuring is the stem thickness. The stem consists mainly of cells filled with water and other things. So once the plant is active, it will use these resources in these cells, and during the day it will shrink. It's a matter of stress. So the more it shrinks, or the deeper it shrinks, the more stress it has, the more the internal reserves of the cells are depleted. At the same time, what we can see during the day here is the SAP flow is going down here quite severely. So what does it mean? It's just when a cloud passes in front of the sun, the main driver of the photosynthesis will be blocked, and we can see that the SAP flow is declining immediately. At the same time, we also see that the diameter and the internal reserves of the cell are recuperating. Then the sun comes back. We can see again internal reserves are depleted. But when the sun is going to bed or going to sleep, we can see that the plant is able to recuperate and even fill its internal reserves fuller than the day before. When we are going to compare this level with the level of the day before, we can see it as a daily growth or daily shrinkage of the plant. And it's also a measurement for the vegetativity or the generativity of a plant. So this is actually the basics of our two lines. What is important to see is that we want a certain effect, a mirror effect. So the higher the SAP flow, the deeper and the diameter goes. So the harder the plant has to work to be able to keep up with the SAP flow. If we look on one growing season, what we will see is that the diameter will grow quite fast in the beginning of the season. But once there are more and more fruits and the length of the plant is also getting bigger, the growth will stabilize. But what is very important is for a healthy plant that even at the end of the season, there will always be a little bit of growth. It's really important. It's as such that we can see a plant is healthy and is not weakening itself. Excuse me. For the daily SAP flow, we can see that it's really during summer that we have the highest SAP flows, but also the highest varieties between dark days and sunny days. So it's really important in this period that the plants are guided well through this period. In the beginning, we have low SAP flow because the plant has less leaf area, so there's less transpiration, and the sun is less intense, of course. And also in October, we see that the SAP flow is lower. We're an international public, so this can shift from month to month depending on where you are on this planet. But this is the main trend we will see here in Europe. Then also, this graph is explaining how the plant is actually growing. So what we see is here a period of fast growth or normal growth. It means the plant is really having a lot of resources, but not a lot of fruits. It means that all the energy that the plant has can be put into the formation of fruit, but also in its growth. Once the flowers become really fruit and they have to grow and take up a lot of energy and water, we will see that the diameter growth will stabilize towards this period. Why is that? Because all the energy that the plant makes, all the assimilates, won't be able to go to the growth because the fruits are taking all the energy of the plant. It's just when you harvest the fruits that the plant is able to put its energy back in its growth, and this we will clearly see this pattern on the plants. Here it's measured on tomato, but also we see the same pattern on bell pepper and eggplant, for instance. Yes. Also interesting, and certainly for, of course, the AQUA4D, is that we can also detect stress with our measurements. And how is a plant expressing stress? It's through a shrinkage of multiple days, the thing we see here. So this example shows an apple tree with a control plant and a stress plant. So from here on, the white plant doesn't get any water anymore. In the beginning, the plant will grow in the same rhythm as the control plant, but after 4 or 5 days, we can see that
Olivier, I do not hear you. Oh, Maxime, do you hear me? Or it's an issue on my side? Raymond, do you hear?
Moi, je t'entends, mais j'ai plus rien. Can you hear me?
Oui, je t'entends.
Okay.
Okay again. C'est bon.
Okay.
So we are at the stress. Was it clear, or till when it was clear?
No, so you were maybe restart your explanation because it was shut.
Yeah, we
Cut.
lost the conversation about the drought stress start.
Yeah. Okay. So so you can see after several days that the plant who doesn't receive water has really stress, and the plant outs the stress always by a shrinking diameter. So every day it loses a bit of internal reserves of the plant, resulting in a shrinkage of multiple days. This is really a sign for stress of the plant. Here it is water stress, but also with viruses or infection or whatever reason that stresses the plant, it will always show stress patterns through a shrinkage of the diameter for multiple days. With our sensor here, we can also already see that the growth is slowing down and the plant is shrinking, but visually, it would only be possible to detect the stress here after 10 days approximately. So here we can see the plant has stress. We can assess that it's due to water shortage. Only then we will give water. But what is important is that you can see here the recovery. It will take multiple weeks even to get at the same level of the control plant, and actually it will never reach the level of the control plant. So this is undeniably a loss of growth, but also a loss of harvest. So the earlier we are able to detect stress, the earlier we can react to it, and of course the less yield that will be lost. Yes. Another example of or what we can measure is, of course, irrigations. So what we see here is we see a substrate that is very dry. So during the night, it's becoming very, very, very dry until here when we give our first irrigation. The first irrigation will make sure that the cells, the internal reserves, will replenish themselves, resulting in a growth of the diameter. But at the same time, because all cells are depleted, it will also result in a slow rise of the SAP flow, making the SAP flow and the diameter increase at the same time. And this is really for us the sign that it's an irrigation. So as such, we can distinguish between other things and irrigations. What we see then is that after the first irrigation, the sun comes up here. We see that the internal reserves from a given moment will deplete themselves again because we have already some level of activity. Then a second water cycle is given. We can see again the similar rise of the diameter and the SAP flow, resulting in a higher SAP flow at the moment. The result of the second water cycle is less than the first one. Why? Because there's already water in the slab or in the ground. And as such, the effect of the second water cycle is less than the first one. Then we see the third water cycle. Why is this line declining so fast, or why is the diameter getting depleted so fast? It's just because the activity is rising really steep. So it means as there is still not a lot of water in the ground or in the slab, that there's not a lot of reserves, and as such, the water will be quickly depleted. After the third water cycle, we see that no more additional water cycles are given through the day. We can also see that the plant is actually following kind of the mirror pattern I explained in the first graph. But what we don't see is when the sun is going down and the radiation is less and less during the evening, we would expect the diameter to rise again. But here, this is not happening. The plant can recuperate only very late in the evening when the SAP flow is really, really low, indicating us there is a certain problem with the plant. The plant is not recuperating here. Why? It's actually an example, so it's quite easy to see. It's because of there is not enough root pressure, there is not enough water in the slab or the ground in order to be able or to enable the plant to recuperate at its level of the previous day. Another factor here can be that there is not enough moist in the greenhouse, or the humidity is too high. So the SAP flow is active for too long of a time before it goes down. So actually by increasing the humidity in the greenhouse, also the diameter recuperation would benefit from it. I don't know if that's a little bit clear or I'm going too far into detail. But these patterns are the patterns we don't like to see because as you clearly can see, we have a shrinkage on these days. And these days are also usually the days we see, for instance, blossom end rot, or here you are really weakening the plant and making it prone to diseases and infections. There are, of course, ways, as I explained, to counter this kind of behavior from the plant. Then the last example I will give before going through your data and the data we see now from AQUA4D systems is actually we can see water cycles, but also, for instance, the effect of tube heating is very clear. We can see here the tube is heating the greenhouse. Immediately we will see an effect on the SAP flow. So we will see an increase in SAP flow and the diameter will shrink immediately. This effect is immediate. So as we can say, like if your crop is too vegetative, we would like to have less growth. So what can we say? We can say, like, instead of making it 4 a.m. make it 3:30 a.m. As such, the diameter will decrease earlier than here, and it won't be, well, it will miss some extra growth, sending the crop or steering the crop more generatively. On the other hand, if the crop is way too generative and you want to have a more relaxed crop, you can also say like, I want a little bit of extra growth. What you can do is put on your tube heating a little bit later, making or enabling the plant to have extra recovery this night, and also steering the plant more vegetatively. Not only can you see the effect here, but when you adapt your steering the next day, you can immediately see what is now the difference between today and yesterday, and is the effect or the changes I made in the steering, are these the effects I desire. As such, we try to shorten really the feedback loop between the actions you take in the greenhouse and also how the plant is reacting towards it. And we hope to increase also the yield and the possibilities for the grower to instantly react towards what the plant really desires in the greenhouse. So these are the basic graphs. I don't know if you have any questions now, because I understand it's a little bit a lot. Otherwise, we can directly go through the data of the trial we have running here in the Netherlands with already some nice results. I guess Olivier will present to you.
So the point of our sensors are really to see which effect has which effect, because this is tube heating, but we can do the same with the screens, but also the mirrors, the windows, the watering, like you see, and like this, we can really monitor each effect and fine-tune it as well to make a really optimized way of growing. And this will be important for the AQUA4D system, but I'll come back to that right now. So we have an experiment running together with Raymond at one of the bio-organic growers here in Holland. And so we have an untreated site and we have a treated site. So this site has been treated with AQUA4D technology water, and this site hasn't been. In the middle, there's some concrete pathway dividing both, but we have both plants are on the same distance from the path, so it's really well comparable, and yeah, it's a nice experiment without much fluctuations, to say it like that. So one of the first thing that really sprung for me in my eye was the daily growth. So the blue is the treated one and the green is the untreated version. So if you look at each point here, this is a day. So if it's under the line, you have a sort of shrinkage. We moved the sensors here, so that's causing the shrinkage. And if you are above the line, you have growth. If you look at both untreated and treated, you can see that sometimes the untreated has more growth, but the treated one has a very stable growth. The untreated ones have a lot more fluctuations and actually a lot more stress compared to the plants with the AQUA4D system. If we go to the next graph, we've not said it before, but variation. So the difference, I'll go back. The difference between the highest point, so here, and the lowest point here, this is the variation. Between midnight and midnight. Variation is a signal for stress. As VPD, they always like to say, the VPD is an indicator for stress. From a certain value on, the plant is stressing. But we see this in the measurements as well. If the VPD remains very low, the plant is not really working and there will be not a lot of shrinkage. So the further the diameter goes, so the more variation there is, we see it as the more stress there is. However, a bit of stress is not a bad thing. For tomato example, for example, you need to have stress to really augment those Brix values and make the yummy tomatoes that we love. But like for cucumber, this is different because for cucumber, it's like filling bottles, we like to say. So this hard work is not really needed because it needs to fill up its fruits as fast as possible. And in these moments of shrinkage in diameter, these are moments that there is not a lot of pressure on the fruits as well, so they cannot fill it up as fast. So if you look here, this is a comparison of the maximum daily variation. So each point here is 1 day, and it actually shows that the plants that has been untreated have a generally less variation compared to the blue one. The treated ones have less variation than the green one. So we can actually say here that the plants with the AQUA4D system, they need to take less reserves to suffice in its daily transpiration and activity, which means that either they have a better root system or it can take up water more easily, which actually falls in line perfectly with what you guys are doing. So it's actually well explainable what's happening here. So there are two effects that we really can see clearly from day one actually, is that, so I will explain the graphs first. The blue line is the SAP flow here, and the green line is the diameter. So the right side is always the treated, and the left side is the untreated version. So you will see at the start of the day here at the treated plant, okay, you see the SAP flow rising. The diameter will start to lower a bit because it's taking up its internal reserves. And then when the SAP flow here, it drops very fast, it can recover very nicely. But when we compare this with the untreated version, you can see that actually here, this is the moment of highest activity, and this is the negative peak from this. But you see it can restore during its drop very nicely. If we compare it to this graph, it can recover somewhat, but this small bump in activity lowers it further down. You see this effect as well, but the distance between this and this and this and this is far greater. So this plant has actually better recovery. So it looks like it can fill its reserves faster, and which is a really positive aspect. We see this here on the 4th of May as well. This is an untreated plant. By the way, these are two measurements where we take an average from. So even if one sensor has a bit of an afwijking, a fault, to say it like that, the other one makes it up for it. So here the untreated, you see that during its daily activity, the trend is actually rather negative. While the treated plant, it's not a very sunny day as well. So the sunny day can really, the treated site can really fill up its reserves and actually have a lot of growth during the day, while the untreated plant is actually shrinking. This shrinkage is not that bad, but when we are comparing the two, it's actually a big difference because we say this is a more vegetative way of growing, and this is a more generative way of growing. It's this last peak towards the evening that's actually one of the lowest points during the day. While here, this large peak, yeah, it drops a bit, but there's so much recovery being done during the day that it actually doesn't matter that much. And we see this every day, actually. There are some days that we don't see exactly the same effect, but generally we can make the same conclusion every time. This is an example of the 6th, so as well a very dark day, but you see a more positive growth trend than the untreated version. If we go at, this is yesterday and the day before, so the 26th and the 27th, I thought it was fun to make a more recent example, where you can see that actually the treated plant, so the blue one, can recover much faster. Already here, I think it's 12 o'clock in the afternoon, so midday, and you see it can recover, while the untreated plant only can recover towards, I think, 4 o'clock or something, which is a lot later. It cannot fill up its reserves again as fast. And we see it at the 27th as well. The untreated plants, they shrink further towards the end of the day, while the treated plant can already fill up its cells here. This is very important because, yeah, you are growing a lot more vegetative, and there's a lot more room for stress. You can punish the plant, you can let it work a lot harder using the treated, so the treatment with the AQUA4D, than with untreated plants. Oh yeah, I'll come to the conclusion later. The second effect, which was really remarkable, actually, I did not expect this as well. If you look at the untreated versus the treated plants, you'll see that, yeah, there's a moment at the morning, like Maxime said, that the diameter will start to shrink. This is coherent with the activity during the day. And what we will see is that the treated plants always, or in 90% of the days, it takes up its reserves much later than the untreated plants. So at some point, there's too much suction force that the root pressure cannot suffice in filling it up, that the diameter starts to shrink. So the earlier we see this effect, that means just that there's not enough water potential or root pressure to fill up its reserves, or to fill it up as fast as it's being taken out. So you see that here the untreated plants already start dropping. They start working. They are taking their reserves again at 5 o'clock in the morning, while the treated plants are only in the at 6 o'clock. I thought this difference was so remarkable that I asked the grower if he was certain that there was no different irrigation schedule, because this is something that we do comparisons all the time. This is not something that we see as often. And it's quite clear. And we see it here as well. This is the 9th of May. We see here around 6 o'clock, the diameter start to shrink, combined with the fast increase in SAP flow. So sun is coming up here and temperature is rising. But here on the 9th with the untreated plants, you will already see some shrinkage at 5 o'clock. This is really, really remarkable because there's not a lot of activity, but still it cannot push as hard as with the treated plants. So it cannot take up water as easy. Again, this is actually an example of yesterday. You see here the untreated plant, and I think it's one of the examples that we see and at the first effect as well. Here you can see at 4 o'clock up, the diameter starts to shrink already, combined with some small activity. But here at 6 o'clock, the treated plants seem to have already more activity, but it's only starts shrinking somewhat past 6. This is really, really important because that means the grower doesn't need to give as much water as it needs, as it's used to do. Because we really like, before there's the first watering period, that it's already starting to shrink. Because this means that the plant is searching for water and making its fine hair roots that every grower so desperately wants, and which is really important. So here you could, maybe give water here. After it, I'm just saying something, maybe here, but yeah, here the untreated plants already could use some extra water before that moment. It's I think it's really remarkable. Also, I want to come back towards the late recuperation, because Maxime said it earlier as well. Such late recuperation or restoration is really closely linked with blossom end rot in tomato, but also in bell peppers. It's a big problem that, the general rule is there's a problem with calcium, but we see actually that the general the problem is that the reserves are not being filled fast enough. So the diameter keeps shrinking. Sometimes it's very closely correlated with the VPD again, but sometimes at 8, 9 o'clock in the night or evening, we see the recuperation. While the earlier the plant starts restoring, the more assimilates can go back to the fruits, which limits the blossom end rot. And this is a case that we've already seen in our sensors. And we could say that using the AQUA4D system, you would have, with the same way of growing, I'm rather certain that you would have less blossoms and rot, which is really a big problem in bell peppers and tomato. So I think you have a good case here to really promote your technology. So I will go to the preliminary conclusion. So it seems that the plants who are treated with the AQUA4D system can take up water more easily, because it can restore faster with a higher transpiration. So there's more root pressure. It has a better restoration towards the evening. It has less stress, and it grows more vegetative. I know from the talk with Charlie and Raymond that sometimes you cannot really see some effects in production, which is rather logical, because you need a different way of growing. The plants that we are seeing here with the treated version, it's maybe very early to tell again, but they have a lot of room to grow. They can really push more generative, more energy towards the fruit, which will cause, I think, a better production compared to the grower with the untreated plants. However, the grower with AQUA4D needs to change its way of thinking and really needs to push the plants more towards its limits to reach that optimal production. So these were some things that we've seen in our sensors. And I know Charlie also asked last time, okay, but is this significant what we're seeing here? But it really is. This is it doesn't have shrinkage, but these are differences that are quite interesting and important to realize, because we are not a fan of late restoration, and we always say to the grower, okay, but maybe you need to raise humidity or give water, also like Maxime said. But yeah, you could give AQUA4D water and it would grow better using the same way of growing. But maybe I'm a bit promoting the technology now, but yeah, seeing this examples and results until now were really eye-opening for me, because I already knew a bit what the effects could be, but that they are so clear really surprised me. So yeah, this is my presentation. I think it's interesting to really follow it up more closely and see how it evolves towards the rest of the season. But I think we really have something interesting in our hands. So yeah.